So yeah, my name's Dan Mazur. I recently started at Singular Software, which is a small startup working on deep learning applications to being able to hear better in noisy environments. So this is, in fact, Bruce's company, and several of my colleagues are here. What we're talking about today is, in general, the nuts and bolts of training neural networks. But in order to guide the discussion, recently a famous machine learning scientist named Andrej Karpathy has posted a recipe for how to do this. So I'm going to go through his recipe, and we'll use it as a sort of guide to the discussion. And yeah, this is going to be a lot more interactive than the normal presentation, so feel free to jump in with questions and comments. And I'll do my best to repeat them. If you have a longer question or comment, please get one of the microphones. Okay, so this slide shows in stock photos how people normally get started in training deep learning models. So first of all, you read books and read articles online and papers and get an idea for how it works. Next step is now you're getting a tutorial from someone. So maybe this is someone sitting side by side with you in person, or maybe it's a tutorial online, but someone has sort of prepared an exercise for you to work through to get an idea of how to train these models. And then the next step is now you want to apply these ideas to your own ideas. And the last step is that's where the frustration comes in, because it turns out that the person who was guiding you through those tutorials and stuff did a lot of preparatory work and made it quite a bit easier for you. So what goes wrong in this normal sort of trajectory of learning deep learning is, yeah, the mentor does all this work, and then that work doesn't generalize to the new problems you want to solve. So it turns out that actually getting these neural networks to train properly is not such an easy skill to learn. You can try and develop intuition about it. So really what you're doing is you're training an optimization problem in these very high dimensional, very non-convex spaces. And so you can try and develop intuition by learning about convex optimization, where there's a lot of theory to guide you. But at some point, you hit the limits of that, and then you might try and get intuition by thinking about it in terms of low dimensions. So these are two plots that are in 2 dimensions, but really these can have millions of dimensions to worry about. So in order to learn this skill, you need to either spend hundreds and hundreds of hours working on the skill, developing it, or you can listen to experts, and ideally you do some of both. So the expert we're listening to today is Andrej Karpathy. He's currently the director of AI and autopilot vision at Tesla. He has a PhD from Stanford in 2015, supervised by Fei Li, who's another very prolific neural network researcher, and the principal investigator of ImageNet. He used to be with OpenAI as a research scientist, and and he wrote this blog post that we're talking about. So yeah, he's an expert, and we will listen to him, or at least debunk some of the things he says. Okay, so here's what Andrej gives as the motivation for writing this blog post. The first motivation is that training is a leaky abstraction. So the definition I put of leaky abstraction is that this is an abstraction that exposes details that are meant to be hidden. So we deal with abstractions all the time when we write software. So you build a class that solves some sort of software problem, and it has some method that you feed it some inputs and you get the outputs, and the outputs are correct because the abstraction is not leaky. But in reality, there's this law of leaky abstractions that says all non-trivial abstractions are to some degree leaky. So that means that it always matters a little bit how that abstraction has been implemented. You can always get some information out about that. So there's no perfect solutions. And it's certainly true that when you're fitting these neural network models, these abstraction leaks become really important. So what you'd like is to just have a fit method, and you call it, and now you have a good model. And it doesn't work quite that easily. So this is my illustration of a leaky bucket saying he's a Keras model, just call .fit. You don't need to worry about how it's implemented. So that's not the case at all. You do need to worry about how .fit works underneath the hood. The second piece of motivation for his blog post is that training fails silently. So usually what's good in software is that often it fails very visibly. So you get a core dump, or you get an exception thrown, or something really dramatic happens, so you know that an error happened, and therefore you can stop what you're doing so that you don't make mistakes trying to go forward despite the error. What happens with training neural networks is you have this huge error surface, this huge array of different things that can go wrong, and for almost all of the things in that array, it'll just fail quietly, and you'll get a bad model out at the end, but you won't know why unless you dig into some of the details. All right, any questions or comments about the motivation?
Might as well start talking now. Just on the unit tests on the model stuff, like this is something that comes up forward. One more.
I didn't have any slides on unit testing.
No, it was there. It was there. I swear. Go one more. No, sorry. Okay, all the way back. One more. What? Another one, and one more. There. Okay. Difficulty unit test model training.
Yeah.
I'm sorry. You actually should try to do this anyway, and the article kind of mentions it kind of in passing. But if you give it something that it should really, really not screw up, like say something that's all zeros, or something that a linear model would be able to do, you should actually just have like a reference test for that. And that's one of the little tricks that I've kind of picked up. Just test to see if it's doing better than random or something like some other really dumb model.
So how many people here unit test their machine learning models?
Okay, but that's not really a unit test.
Yeah.
Yeah, well, you unit test like all the pre-processing code, but you also have like not regression tests, but kind of like a reference test as well.
Is that just like a performance test?
I wouldn't call it a performance test. I would just say that it's like you're just seeing if it's better than baseline. But you want to set up the expectation before you actually like start writing stuff.
Yeah, I wish I had said who here writes automated tests for their machine learning models. Good. Yeah, it's good practice, and it saves a lot of these errors. But like Andre says, it's not easy to do. It's not easy to get good coverage for to really cover this huge error surface. It's just impractical. Any other questions, comments? Okay, so here is his recipe. So here's the things he's trying to achieve with the recipe. The first is to take these two ideas, leaky abstractions and silent failures, very seriously. Second thing is to encourage building from simple to complex and not trying to leap too quickly into doing complex things. And then working via creating and testing hypotheses. So basically applying the scientific method to the development of these machine learning models. So here's the recipe in bullet point form, and then I'll dig into what each of these things mean in more detail as we go through. So step one is becoming one with the data. This is just inspecting the data, understanding what quirks it has, finding if there's any quality issues with it. End-to-end skeleton and baselines. This means getting sort of a minimum viable product style thing working end-to-end that doesn't have any bells and whistles, has a really simple model. Step three is to then overfit. So you have your framework set up. Now you want to build a model that overfits your training set without worrying so much about how it does on the evaluation set. Then you regularize. So now this is trying to get good generalization performance with your previously overfit model. Step 5 is tuning, so hyperparameter tuning. And then step 6 is, so in the blog post, he calls this squeezing out the juice or something like that. He has some vague name for it, but basically the two things he mentions are building ensembles out of the models you build and trying really long training sessions. Okay, becoming one with the data. So this is another plot that was used in an article about Karpathy, talking about how he loses sleep in the different phases of his career. So when he was doing his PhD, he lost all of his sleep, worrying about models and algorithms. Now that he's at Tesla, out kind of in the real world, working on real world data, now he realizes that the thing you spend most of your time worrying about is the data sets themselves and the quality of the data you're using. So the quote from the blog post that he uses is, the neural net is effectively a compressed/compiled version of your data set, which shows how important he thinks that data set is.
To be fair, his PhD was using ImageNet.
Yeah.
So the data was there for it. You're supposed to repeat that.
Yeah, exactly. So yeah, when you have like a nicely curated data set, that's one thing someone else has worried about, and now you don't have to worry about it. When you're directing AI research at Tesla, now you have to worry about the whole thing. But yeah, the data set is a very important part of that, of the things that keep you up at night.
Like, as long as you're just not faculty, it's enough for you to have to worry about that stuff.
Yeah. Okay, so he's a bit vague on exactly what it means to become one with your data. So he mentions a few things. Looking for data and labels that are corrupted somehow. Looking for data quality issues. So I think he mentions kind of plotting histograms and plotting distributions to see if there's any strange outliers that shouldn't be there and stuff like that. Looking for variations in the data that are, so some of them are going to be important for solving the problem that you're working on, for the task that the machine learning system is going to learn. And some of them you should be pre-processing out. So there's some things that you think those aren't going to be important, we should get rid of those. Yeah, go ahead.
So that list kind of makes it sound like you're looking for problems and figuring out how to work around them or whatever. But I think it's just as important to get close to the data so you understand what you've really got and what information is actually there and what might not be there, and how can you get the most out of it. I think one of the things, observing all these Kaggle meetups that we've talked about over the years, the thing that I've learned the most is people spend a lot of time looking at the data. And obviously they find a lot of data leaks. That's one of the outcomes that happens in Kaggle competition a lot. But even when they don't, it informs the models that they build around it. And I know in competitions I've participated in, I try to pay attention to the data, but other people find something that I missed completely. And it turns out to be really pivotal in being able to use the data to get the results. So it's good. I think it's underappreciated.
Yeah, and one thing he does mention in the blog post is so when we talk about a future step, he talks about initializing the weights and doing that in a clever way. And what he means by clever is actually using what you learned when you were inspecting the data in order to choose better initializations of the weights. So does anybody have tips and tricks for understanding your data set?
I just wanted to comment that I felt the advice that he gave in this space was maybe strongly biased towards computer vision problems, and in particular maybe simple or layperson computer vision problems, where it is very possible to kind of next your way through your own data and learn what it means for a label to be and to see things that are labeled incorrectly and so on. And I think that's not necessarily the majority of problems. I mean, personally, I work on computer vision problems at the moment where I can't actually look at an image and tell you what the label is because a medical expert gives it that label. And so I have I certainly still have the ability to look and find priors or structure, things that might inform pre-processing or data augmentation, but I'm actually not able to tease out the essence of what it means to classify an image. And then furthermore, if we throw away computer vision entirely and we start to consider non-visual tasks on tabular data, I think the task, it's a totally different beast, right? Still needs to be done. I like to complain that I think that machine learners trained in the computer science department don't graduate with any idea of what it means to really analyze a data set and reach conclusions to inform business decisions, which I think is what you need to do here. And I think most problems in this world are in fact tabular data problems, and actually probably maybe not necessarily neural network problems. But if you were going to, I don't think he offered a lot of advice in that space. But you still need to become one with the data. You still need to figure out I was actually even earlier this evening commenting the first thing I'm going to find when I look at your data is the mistakes, right? The missing values or the places where you only provided a portion of the data, right? Like, oh, for some reason, like in the final quarter of every fiscal year, you only give me half the data. And like, you need to know those things if you're building models. And I don't think there's any solution except like lots of time.
And I would actually say that those are the easy errors to spot. Like even trickier errors to spot are data issues to spot are distributional issues. Like oftentimes you are given like a bunch of label data and okay, build me a model to do something that's going to be running in a completely different scenario. Like this label data here, the distribution of it doesn't match at all what you're actually going to see in production, in a production environment, or whatever is your use case. So like you doing your splits here, however careful you are about them, it's still not going to be anything like comparing to where your models are actually going to be doing the prediction. So those are really hard to spot. So that really requires an understanding of the use case.
I want to expand on that point a little bit. What I spend a reasonable amount of time doing in every project is understanding how the data itself was generated in the first place, as it gives you a very good idea about what potential biases could exist, how there could be inconsistencies through time or inconsistencies in other cases as you're talking about. That's it.
Yeah, and further on that one with regards back to the images and also other sensor captured data, talking to companies and messing around with different data sets, it's pretty common to see people not understanding the source of the data in terms of, I've captured all of the class N examples with this camera. I've captured all of this other class with that camera. I'm doing inference in the world with some completely other camera. Why doesn't this work? It happens all the time. I look through data sets and you can see like the colored shift, the noise floor, everything's completely different between the classes or between large amounts of the data sets that they're using because they haven't paid attention to that while they were putting together their data sets. And that makes a huge, huge, huge difference for your model. And it's also really hard to fix that with augmentation after the fact.
Okay, it's a lot of good points. Sorry, I'm jumping in, Alexei. There's a lot of really good points. My own experience with data inspection comes not necessarily in this kind of linear flow that it was originally laid out in, but almost after I build the models, they kind of help inform which records. So I deal with a lot of mislabeled data, and it's important to like inspect the labels that the model is actually getting wrong to kind of check to see whether the model is actually incorrect or not. It makes validation difficult.
I'll jump in on that pass to say, like, I got another way I think this is biased towards like layperson vision problems is there's no kind of reference to domain knowledge or domain expertise. Like, there's this sort of like almost assumed that like I have all the knowledge I need in order to make judgments and understand the data. And so that whole interaction with someone who knows the problem space, knows the data generating function, or knows like can guide you towards how they would solve this problem today. There's no commentary here, and it's an entire subject into itself.
I have a quick little tip here. So first, a warning, like, it's not mentioned in the article, and I see this a lot, people just grabbing, say, the first 100 examples in any data set. Don't do that. Like, actually randomly sample from the data set, because oftentimes, you'll get like a really weird class imbalance where it turns out, everything of one class is just right at the start, and you're going like, oh yeah, it's like this, but it's not. So always randomize. And another thing, and like, Excel is useful for this kind of stuff, right? So take a big chunk of your data, like say like 2,000 rows or something like that, color code based off of like what you want the label to be, and start like looking through, okay, why are these things green and those things red, right? And, as they say in the article, or Karpathy says, like, we're pretty good at like seeing patterns, right? But not when it's just like a field of numbers. Like, I don't know about you guys, I just kind of glaze over. But as soon as you start seeing like, oh yeah, it turns out like, all these rows are red when these values are like this or like that, right? That gives you a pretty good intuition about what's going on in your tabular data, and then you can start actually feeding it into your models or whatever.
Sorry, just one thing that I noticed, he doesn't actually mention it, but I think all he's talking about is classification of images using neural networks. He says generally using neural networks, I can think of at least a dozen other applications that these things would be completely wrong. Like you just can't do it. Like if you're training GANs, like you just can't do it. If you're even doing object segmentation or something like that, I think you need a new set of rules. So maybe it's good to, I don't know if you agree, do you feel it's just mainly for classification?
Yeah, I mean, that's his experience, right? So he's speaking about his own, like how he approaches his work, and his work is in computer vision. So the article has a clear bias towards that, which is fine.
But classification is a small part of computer vision as well, right?
I see what you're saying, yeah.
I would say it's the most trivial part of computer vision. Fair enough, yeah.
I have a comment to make too. Depends again on which domain you're in. So with speech data, I agree to this is experience coming from dealing with 1,000 hours or more of speech data. Speech data varies with your surroundings. Again, with the sensors it's been captured on, the sensors with which your models kind of get biased. So again, there are entire PhDs written about how to compensate for all the sorts of variations you actually see in an audio signal, so that you can do at inference time there isn't a train test sort of mismatch. So sample fairly randomly throughout your data set. The other thing is with computer vision, there's problems like pose estimation, detection of people, not just classification. Lots of important problems. I don't know why I started off on that, but yeah.
Okay, we'll move on. Step 2 of the recipe is building the end-to-end skeleton and baselines. So this section is full of tips, like rapid fire tips from him. So I pulled out a few of the ones I found most interesting, but it's definitely good to actually go and read this section of the blog post in detail. So some of his tips, in order to train a correct simple model, ignore anything not necessary for training a simple model. So do that, minimum viable product, just get an end-to-end system working and working correctly. Implement evaluations early on in the process. Initialize thoughtfully. So this is where he gives some tips on how to use your knowledge of the data to choose better initializations.
Can I just talk about that one for one moment?
Go ahead.
I thought that was interesting because, I think it's really common practice to kind of whiten your data. So, if I'm doing a regression, sure, I could work out what I think the mean prediction should be and then later take that number and initialize the bias in my fully connected. But I can also just normalize my regression target to be mean 0, and then I don't do that. And so I found that one a bit strange because I think it's much more common practice to kind of solve that problem in that way. I don't know if anyone disagrees with me, but. Okay.
Sorry, are you saying it's a good or a bad thing?
No, I'm saying that I don't think people generally solve this problem by initializing thoughtfully. I think they solve this problem by normalizing their training data in such a way that they don't have to think about it.
When you're dealing with class imbalances and you're doing a classification problem, how would you go about not doing it?
Yeah, maybe there's an example where you would initialize your biases if it was important.
So when I read it, that's what I was thinking of, and that's something that I'm not currently doing. And I'm doing classification of text, and it's not an equal distribution. So I thought that was actually, that's something I took that I didn't think of. And these are the trains. Shoot. I essentially just think that, yeah, maybe in a classification sense where I guess you can initialize your final softmax layer, or is that the layer you would initialize? Anyways, I thought that this was a good point.
Yeah, so the classification case is one thing he brings up in the blog post around this point. Go ahead.
One thing that I do think that is typically overlooked is like that second point there, the implement evaluations. Many people focus on like the metrics and all, but like you really should be careful about how you pick the samples that actually go into those evaluations. Again, going back to those, I don't know, maybe I'm just paranoid because my specific area, my training data, like the label data that I have, the distribution is completely off from the distribution at actual production. So one really needs to be careful about how you pick the samples that are actually going to go into your evaluation data set and how it's distributed.
So confirming loss at initialization. So this means before you do any training, does the loss you get out at the end of your neural network make sense in terms of if you're doing a classification problem, you should get out like a random basically the prediction should look random initially before you've done any training. He talks about doing input independent baselines. So the example he gives is sending in all zeros into your neural network and seeing what prediction it gets out, and then thinking about that to see if that makes sense. I think this is, again, before training, if I remember correctly. So like with randomly initialized weights, if you send in all zeros, does the output make sense? It talks about overfitting one batch. So one
Go back on that. How would you find makes sense? Could be the majority class.
Yeah.
And that's before training. Yeah, but he also says to kind of hand-tune the biases. So on the first round of training, you don't have that huge dip and think that you've really learned something. So I think that's one of the things that he's trying to get at. He does it differently than like I've seen. I think Alexi was talking about a similar thing as well.
Yeah, so one sort of recurring theme of this blog post for me was he gives a lot of advice that seems unusual and then it's not fully explained. So it's some stroke of genius that he's figured out that you wish he would explain more.
Yeah, I'll definitely say, like, I mean, if you're doing like inception style image normalization, so that all zeros means this image is like 1 to 2.5, whatever, RGB or something, like, I have no interest in what my model outputs for that image. I don't think that's informative. I think I've had models spit out nans for that as well, and I don't think that's like a useful test.
Okay. Yeah, so one thing we're going to do in a future step is try to overfit our training data. So one thing you can do in this step is make sure that you can overfit one batch, just make sure that aspect of training is working for you. Verify that while you're training, you're actually getting decreasing training loss, which obviously if you're not getting that indicates some sort of problem. Visualizing the prediction dynamics. So this is, as you train this very early model, you want to visualize how it improves as you increase the amount of training you've done. And then another interesting point he makes is to use the backpropagation to debug unintended dependencies. So the example he gives is making sure that you can so you set the loss to be the sum of all the outputs, but only for the ith example, for example, in a batch. And then you do your training and you make sure that the gradients that you get from the backpropagation should only be non-zero for that ith output, given that loss function. So that's one way you can test to make sure that there's not some strange dependency that you haven't accounted for.
So I have a question for the group and for you as well, Dan. The visualized prediction dynamics seems like it can be expanded on in a lot of different ways, and maybe some people have figured out tricks or different ways that they find useful for visualizing their prediction dynamics. Like, does anybody have any comments there? Yeah, Andrew.
So there is a from the deep learning summer school in 2015. There's a really cool talk by Leon Botou. He actually talks about one thing that you should do while it's training is to actually look at the dynamics. I actually do this like in log files, where for each layer I sort of set the max, min, and the max and min so the dynamic range of the values as they're propagating forth, propagating back, and the values of the gradients themselves. Because if your gradient sort of blows up or is really tiny, just sort of plotting the dynamic ranges of values of activations can be a huge help, especially in diagnosing things like NANs. And one other thing I really agree with is, I mean, assuming this is a classification problem, is to look at the values before your softmax, because it's after the softmax where your loss gets calculated. But then again, before the softmax, if your values are out of dynamic range, you're essentially taking an EXP to something. And if it's outside the value of machine precision, everything's basically going to break, right? So, and then your loss doesn't get calculated, you get a bunch of NANs. So again, check for dynamic ranges, check that they're within sort of known bounds within with machine precision. And with regard to the, set the sum of all outputs to the ith example, I think that sort of intuition also comes from one of the other things you do when debugging a backprop, if you've implemented it right, is to actually sort of like set your deltas. It's called numerical differentiation. You can approximate numerical differentiation. So yeah, that might be coming from there, but sorry.
Yeah, so the question was, is it prediction dynamics or something else dynamics? And I think you could look at the dynamics of everything, right? So looking at the dynamics of the weights, the dynamics of the gradients, all these things are important, especially like just to confirm that your network is training the way that it's meant to be training.
What does that even mean, prediction dynamics? I don't understand what that means.
How they change as you train it.
Change what? Oh, the classes, how they change?
No, like how everything in the network changes as it's training.
Okay, so it's training dynamics. Okay, is that what it means? Okay, that's it's just odd to call it prediction dynamics.
I found this confusing too. But like reading through this paragraph a couple times, I think what he's saying is, so he has like a very small test set that he's looking at that he can actually like, actually see all of the images at the same time. And then he's just seeing like how the classifications are changing on that small test set, I believe, or it's confidence, I guess you would actually have. So like the probabilities are coming out of the softmax. And then, one of the things that would show would be like, okay, these two categories of images are probably very similar, so it's going to take a lot of time for this to actually resolve. I think that's what he's getting at, but yeah, it is kind of confusing.
This might be biased by my medical images. I've not plotted like images and classifications and seen those change over time and found that informative. But again, like I can't tell when I look at these images, but I have seen it very powerfully in object detection. Like, so when I see whatever region proposals or bounding boxes and so on, I can definitely see a kind of a start from crap and start to converge to something and have some kind of confirmation that my model's actually learning something. So I've very much seen value there.
It's on. I can maybe comment on your question on is how to look at prediction dynamics. So say you have a tiny test set, right? And you are saving the classification results of your model through every epoch, right? So you'd want to make sure that as the epochs progress on your test set, the classification for a particular set of examples actually goes from something random to something extremely strong. An example of this is actually in speech recognition models use an algorithm called connectionist temporal classification. If you go read Alex Graves' thesis, he actually has an extremely good example of how the models learn as the epochs progress, and that's basically prediction dynamics of how the model learns as the epochs progress. That's what I would think.
Okay. Oh, go ahead.
So I found a lot of these to be very clever, especially when he focuses on the initial conditions and, like giving it something and see what comes out. But I was wondering, like this article was very neural network heavy, and that's what he does. I was wondering, outside of that domain, how can some of these apply, or how can like good practices apply? I can think of like overfitting like to be a very, very general thing. You should get your thing to overfit, and that's a good sign. But what else?
So is the question what from this article applies to?
Yeah, what can you transfer learning? What can you transfer from these things that he does on neural networks to other things, to other problems?
So one thing I just immediately comes to mind is the whole sanity check, as they call it. Put in zeros or put in something else that you know what you're going to get out of it. I think that's pretty typical in all classical other things.
I think. Sorry, I'll just make a comment. I think the structure of the recipe applies to all machine learning. So maybe with the exception that depending what you're doing, you're not necessarily trying to, like if you're working with a random forest, you're not necessarily trying to overfit and then regularize. So that's something that's a bit unique to neural networks. But yeah, this sort of framework applies. Certainly the advice that's in regularize, hyperparameter tuning, and ensembles all applies.
Whenever I'm working on just a classic machine learning model, I always like to start with something that I call a dummy model. It's not even machine learning. It's if you were just dumped on this data and you had no background in data science whatsoever, but you needed an answer, what could you come up with? And use that as my baseline instead. It's so easy to see maybe you're making a classification and you have 50-50, so you kind of use that as your baseline, even though a data analyst 2 weeks into their first job could get you 70% without really much effort. And that sort of changes how you view success as you start to build your models.
Just to add on to that, scikit-learn has actually implemented dummy models, and I highly recommend that people actually use them. It's kind of tucked away in the scikit-learn documentation, but it has all the classic, take the average, take the max, whatever. And I have found that to be actually really, really good, but also really dispiriting, because you think you're doing really awesome, and then you actually just run it against just the average and find out, not so much.
After sort of working years with speech, I moved to another domain where I knew nothing about. So this is data from wearable devices. I found random trees to be extremely good models that overfit to give you that first baseline, actually. And then, so I was literally plotting, 100% overfit on these models to actually predict what they had to do. And then that kind of gives you a sense of your data and your models. So simple models and overfitting them is actually a really good way to start.
All right, so at this point in the recipe, we have our end-to-end framework set up, and we know that it's correct because we've done a lot of validating. And now what we want to do is dig into starting to build the model, and the first step of that is overfitting. So building a model that will do very well on the training data without worrying so much about how it's doing on the testing data. So the idea here is that with these big neural networks, you should be able to memorize the training data set if you try hard. And if you're unable to do that, that might mean that there's a problem. And we know that there's lots of techniques for regularizing these things after the fact. So the first step is to overfit to make sure that we're at least capable of doing that. And then once we have our overfit model, we will then proceed to regularization. He has a variety of tips for how to achieve this overfitting. So he starts with a model from a recent paper on similar data. So he's working in computer vision, so there's lots of options for him in that space. So yeah, he starts out with something he knows, a model type that he knows works, an architecture that he knows works. He says Atom is a forgiving optimizer. So at this point, he's using Atom, and he's using a very specific learning rate, 3 × 10⁻⁴. So he doesn't necessarily say where that number comes from, but he likes it. It's a joke, but it works. Sorry? It's a joke, but it works. What's the joke?
I don't know. He just posted on Twitter one day that's the rate to use. And then everybody was like, oh, that's the rate to use. Later down the thread, he's like, by the way, that was a joke.
Okay. Yeah, so I guess good to be skeptical of everything all the time. Complexify one thing at a time. So this goes back to kind of treating this like a scientific process. If you add too much complexity too fast, you want to understand what you did or why you broke it. And he says he doesn't trust the default learning rate decay. So he disables it during this step, and he's going to tune it at the end, I assume when he's tuning the hyperparameters. So for overfitting, he just disables learning rate decay. Go ahead.
Sorry, there's just a couple of things I'm still confused about. So at which point did we switch from the super simple model to the recent paper to do overfitting? And also, if you use a super simple model, that by definition means you can't overfit. Like, so you want like a medium model to overfit and then switch to the recent one? I don't quite understand that train of thought.
Yeah, so where we switched was when we switched to step 3 from step 2. So step 2 is about building the simple model. Now in step 3, now we're going to work towards building what will likely be a complicated model. So as a starting point for that, he chooses a model from a recent paper. And I assume what he means is an architecture from a recent paper.
Does that mean, do you remove all the regularization at this point so that you can overfit?
Yeah, I believe
because in a recent paper, presumably has a lot of regularization already built in, right?
Yeah, yeah. So while your goal here is to overfit, so maybe you can overfit with all the regularization stuff still in there. But if you can't, then you just start disabling it to make sure that you're able to overfit, knowing that you can add it in step 4, which we're about to get to.
Yeah, the goal there is to make sure that you have high enough capacity in your model.
I was going to say that, so start from a model from a recent paper on similar data, like no, finish there. Really, I mean, like the process is definitely not like that I take the work that other people have done, try it out, and then start coding my own neural network. Like, especially in computer vision, like basically never do that. So I definitely finished there. I agree completely about Atom and complexity and learning rate decay. About overfit though, I mean, again, like most CV practitioners, I think are going to be, like they're often going to be fine tuning pre-trained weights. And for whatever reason, those things overfit like crazy, like in no time at all. So like, it's almost not an explicit step. It's just going to happen like the first time you run it for any length of time at all. And then like, I'm not sure I agree about switching all the regularization off, like probably in some domains, but actually in computer vision, like I just know that I'm going to augment and I'm going to like horizontally flip my images or something. Like I think it's silly to sort of like turn that off because I'm like, oh, we're not going to regularize. First, we're going to overfit. I mean, I wouldn't want to be too pedantic about these rules. Just like do the obvious thing straight out of the box, I think. No, I actually never use weight decay, so there you go. So it's like a per regularization decision then. I wouldn't just switch them all off like blindly.
Yeah, I think the counterpoint to that point, so why you want to do this instead of just skipping ahead to just getting on with the model is by doing this overfitting step, you're demonstrating to yourself that you're able to do it. So you validate that you have the right capacity, and you validate that there's not some bug that's going to silently fail that you won't notice. So this is a kind of a validation step. Mm-hmm. Yes, the comment there was checking that your optimizer is working.
Yeah, but you do that not just to make sure that the optimizer works, but also that you do have like a high enough capacity architecture that allows you to actually overfit the data, like that you have high enough capacity to aspire to the possibility of actually fitting the data, like solve the problem in a way. It's kind of odd way to say it, but that's the whole point of being able to overfit. Make sure that that you're basically limited by variance. So that's when you start turning on regularization. And I would say that you should still like worry about augmentation and all in certain cases.
Since we're at Kaggle, I was just going to say, like, I am trying to overfit one batch on my point net implementation for the molecule competition. And it doesn't. It fits very well, but it doesn't overfit one batch, and that's very interesting. Of course, I'm straying into the dangerous territory of hand coding your own neural networks, but that is actually very good advice.
A lot of the speech processing we do, it's actually hard to get things to overfit, which is an ongoing frustration of mine. But I wanted to go back to a point that actually Lexi made about the first bullet point here, start from a model from a recent paper. It was about the only advice in this article that didn't kind of resonate with me and I didn't really agree with. I mean, the goal here is to get as simple a model as you can that will overfit. And the way to get there, like if you're starting with a recent paper on similar data, it's typically like super complicated, and the way they beat the state of the art was to do something amazingly complex. And I'm just not sure that's a good starting point necessarily. What might be a good starting point is to read that recent paper and see what they used for benchmarks, because they're typically benchmarking against a much simpler model, and that may be a good place to start and go forward from there.
Yeah, and this might be another area where the advice is heavily biased towards computer vision problems specifically, where the state of the art is quite mature relative to other types of neural networks. Okay, so now we have an overfit model. The next step is to now get an actually good model. So we have to regularize to prevent overfitting. So regularizing is this umbrella term that says it means anything you try and do that prevents overfitting, basically. So he gives a bunch of what I sort of considered standard advice, and you can disagree with me on that point. So collecting more data, doing data augmentation. So in computer vision, that's like flipping the images or shifting them or zooming in, cropping them. Using a pre-trained network. Reducing the input dimensionality, so doing some sort of feature selection so your input dimensionality is lower. Reducing the size of the models. Using dropout, using weight decay, stopping early. So these, I think, are all kind of standard regularization strategies for neural networks. So I won't spend too much time on that relative to what I think is the more interesting advice he gives. So he suggests smaller batch sizes. And the justification he gives for this being a regularizing technique is that it causes more wiggles in your gradient calculation. So yeah, it tends to be basically more volatility caused by just having a smaller sample size. And he says that somewhat corresponds to stronger regularization. I feel like some people in the back have comments.
Yeah, so in that case, it's more like try to strike a balance between exploration and exploitation there. Like the ultimate exploitation would be like actually compute the full gradient on the whole data set. And the smaller your batch size, the less accurately we're calculating that gradient, which introduces some stochasticity on the directions, which kind of encourages exploration, which in principle allows you not to get stuck in local optima. So it does have some effect on regularization. It's kind of an exploration thing. Trying to strike a balance between exploration and exploitation. The smaller the batch size, the more you're going to be bouncing around. That's why I think he's saying wiggle the gradient calculation there.
I'll just check in that, I mean, in my experience, I can never fit as big a batch as I want to with my big fat computer vision models. So I'm rarely picking something smaller, I guess. But when I stray away from like image classification into something else, like my point net for molecules, suddenly I can put too big of a batch on my GPU. But
that said, more exploration doesn't mean that's a good thing.
I've found generally with image problems, you can compensate for that by just cranking up your learning rate and end up with the same result. So there's like a pretty wide band when you compensate the two. So I don't know if that actually makes a difference in practice if you linearly increase the learning rate to match your batch size. In the other direction, it usually results to the same if the multiply of the two is equal.
I guess also vision problems. In vision problems, also the size of the model can be relatively small when you compare with, like, say, text or, in some cases even speech.
This is the most counterintuitive advice I actually found in the whole thing. I don't know. I mean, I think all of the advice he gives is a little bit like hand wavy. This is the cult that works for me. And I don't know, without running some sort of experimental comparison to compare what effect the batch size has on where you wind up with an equilibrium, I'm not really convinced one way or the other. And my feeling is it probably doesn't matter a whole lot. There's lots of different ways to add noise to your process other than the batch size. So yeah, whatever.
There's a few really good papers on that have all the charts.
Yeah, this is a somewhat well-known behavior in optimization in general, not just machine learning. This of a subset, like having that you have a smaller sample, a smaller sample of your actual overall objective function, introducing more like jumping around and having this regularization effect is a phenomenon that's fairly well known in optimization and in some inverse problems. Same thing with the early stopping. But I guess it's just different area.
There's a mic behind you.
So whether the batch size is small or big, I think it's relative to the size of your data. Is that correct? Or is that an absolute thing? Because I feel like depending on how much data you have, it means different things whether you take a small batch size or a large batch size.
Yeah, I mean, you can choose a large or small batch size. It's pretty independent of the total size of data.
Yeah, but whether or not you should take a, let's say, small batch size, I think it depends on how much data you have, I feel. Is that correct?
I think only at the extremes.
Yeah.
At the extreme small data set.
Ross says only at the
I think
extremes.
only at the extremes, at least for image situations. I don't know how text or other models would be. But just one Kaggle thing, if you do find a model online or in a paper that you really want to try and you see that it was trained on a TPU with like 4,096 batch sizes and you've got a lowly 1070 and you can only like manage 32, take their batch size over your batch size and then decrease your learning rate by that much, and you'll end up with a result much closer to theirs.
That's a nice rule of thumb, because that actually is related to what the batch size is actually supposed to mean. Like in the end of the day, like you have a loss function that's a huge sum of like smaller losses, like the per sample loss, and this batch size is supposed to approximate, like to approximate that overall average. So like the way that you should think of it is as an approximate, like as a small sample of that overall average. That's how people actually prove bounds on like what is a small or big batch size, but that's getting closer to research, yada yada. That are that's actually related with how fast a sample approximates an expectation. That's actually related to Monte Carlo. Yeah. So that's where the square root shows up.
So to me, what that means is essentially that your batch size should depend a lot more on the distribution of your data rather than the actual size of your data set.
If your data set is too small, you won't get a good estimate of its, I guess, distribution.
That's a different problem.
It is, yeah. But then in that case, to get anything reasonable, you might need it big enough, like you might have to put all of it like in one batch if you can. Then you don't want to reduce your batch size to like 5 images. You want to keep it to a minimum, I think, to like a minimum has to be larger than a certain amount. But I guess that's what he said. Like at the extreme limits, it makes sense to do it, but maybe in general, it doesn't make a difference.
Yeah, that's just like if your original data set can vary wildly, which is not typically the case.
Yeah.
Okay, I think we'll move on from that point. So another thing he says for regularizing is, so the usual advice is if you want to regularize, you should use a smaller, less complex model. But he gives this advice, which is use a larger model, but combine it with early stopping, because apparently large models have better early stopping properties. So this can be a way to regularize as well. Any comments on that one? That's weird. Yeah.
On the small versus large model thing here, I feel that he didn't spend enough time talking about this. It's fairly non-rigorous theoretically, but in practice, it feels like there's like a Goldilocks thing with a just right model size. If you go too far on getting small, it actually is way harder to train well to generalize, and you end up fighting it. If you go too big, it's harder to train. There's like kind of an optimal, like just big enough, probably in relation to the size of your data and the characteristics of your data and the problem you're trying to solve, where it just trains really nicely and generalizes pretty well out of the box and has some characteristics like self-regularizing, as there's some papers trying to justify this. And there's the new lottery ticket initialization papers that have been doing the rounds about like, if you have enough parameters, you'll end up with some initialization subtrees within your network that just start off doing well right away, and they always continue to do well, and like it's like winning the lottery. And so there's all sorts of crazy weird things, and there definitely is an optimum point where if you just pick a ResNet 34 for a reasonable size image problem, it's probably going to do better than if you try to go smaller than that, and definitely than if you try to go bigger than that.
Depending on the problem, there can be alternatives to going to a smaller model to regularize. Like there can be other dimensions of your model that you can make smaller. So we do a lot of encoder decoder stuff, and if you, for example, reduce the size or the dimensionality of your latent space, that's a way to force to kind of put a regularization on the model. But the model itself can be as complex as you want. I don't know if that made sense to anybody, but there's other. It can be helpful to do something smaller, but it's not necessarily a fewer number of layers or parameters in the model. It might be some dimensionality of some intermediate stage.
Okay, another bit of advice for regularizing. He says unsupervised methods are overhyped. So don't get too excited about these. So obviously in natural language processing, all the state-of-the-art models are using pre-trained things trained on huge corpuses. He says it works in NLP because text is very deliberate with a high signal-to-noise ratio, which I guess is less true in computer vision. Anyway, so this piece of advice I think is quite domain-specific. But it's also true that in NLP it's working way better than you might expect.
In NLP, the model sizes are typically way larger as well.
Yeah.
So just a practical question. So if you have, let's say, 100,000 images and only 5,000 of them are labeled, so is he saying it doesn't make sense to make use of the unlabeled one in any sort of clustering, semi-supervised way? It's not going to be worth it? Just throw away those? Or it doesn't seem intuitive to me at all.
I think you would say just label them. Like I've done this before where I've tried to do a semi-supervised thing and it just did not work. So I just spent some hours actually hand labeling it, and it actually did work a lot better. Yeah.
I would say if you have so few actually labeled images, just get a pre-trained network and use that as your feature preprocessor, like feature transformer, and train a much smaller model afterwards.
The papers that I've read recently in this domain for images, where they succeed tends to be in the really ridiculous proportions. So they push CFAR to the point where they have 20 labels from each class or something, and then they treat the rest as unlabeled, and then they perform way better than any other alternative. But I think the real world looks more like the 5,000, 95,000 case, and yeah, I think the gains are pretty small, overhyped. Yeah.
I took his comment to not be a knock against semi-supervised training or unsupervised training in general. I think he was talking specifically about unsupervised pre-training, which I gather used to be a sort of a normal thing to do, and maybe some people still try to do it. I think he might agree. I don't know. Maybe it doesn't have so much image classification, but there's some pretty interesting work that's going on in semi-supervised training and fully unsupervised training these days for the kind of signal problems that we're working on, for example. That I don't think he's knocking that. It's just this pre-training stage.
Yeah, to add to Bruce's point, the entire deep learning thing started with RBM pre-training, which is restricted Boltzmann machines. And I think he's probably hitting at that because as a grad student, I spent a lot of time doing RBM pre-training just to discover that people were publishing the fact that if you had more data that was supervised, you might as well make use of that because you have diminishing returns on an RBM or an encoder, autoencoder style pre-training, which is unsupervised. So those do have diminishing returns in other domains as well. So I think that's what he's hitting at, as Bruce said.
Yeah. Okay, step 5 of the process is tuning. So specifically hyperparameter tuning. So his recommendation is random search over grid search or Bayesian optimization. So he references this paper for why random search is better, Bergstra and Bengio 2012. And the idea here is usually when you're training neural networks, you have some hyperparameters that are unimportant and only a few that are really quite important for going to make a big difference in terms of the performance. So when you look at what happens in this sort of toy situation where you have one unimportant parameter, which is the vertical axis, and one important parameter, which is the horizontal axis, if you choose a grid search, you're just sampling the same 3 positions of the important parameter over and over. And in the case of what that means for your loss function up here, you're not really finding the best point of it because you're sampling so few points. If you were to do it randomly instead, you'd do a better job because now you're sampling let's say, 12 different points of that important parameter. Yeah, David?
This is just me being a little bit pedantic, but because in most practical circumstances he'd be correct on this, but asymptotically it actually reverses. So as you get a better coverage of the parameter space, it actually becomes better to do a grid search than to do a random search, because you're more systematically covering areas and not over covering like smaller sections, which might matter less.
Yeah, but I think the argument here is that so often your hyperparameter space is quite large,
Yes.
and you really can't sample it properly. So random tends to do better in that case,
Yeah.
I think.
Generally, and in all practical circumstances, I agree. It's just not always true.
3 words, curse of dimensionality.
Yeah. That paper is a really great one to read. I believe it's in that paper where they actually show that, like, in basically all cases that have to do with hyperparameter optimization, a random is better. And the reason why is it's not just that it's like a very large space, but it's also like a really bumpy space, right? And by the time you get down to the like level of granularity to actually find that little bump, you would have found it a lot faster in random search. So I have done quite a bit of like work on this, and every single time, what is better? Well, not every single time, sorry. Oftentimes, what is better is just running random search for a longer period of time than implementing your Bayesian optimization or whatever, which is really sad because there's a lot of really cool algorithms. But random is just like really, really good. Pure random, you don't know anything about what happened before. Like what makes that really great is you can actually just like run it on a bunch of different computers all at once. And you don't learn anything about the distributions, which is really unsatisfying, but it still works.
Yeah. So we have 10 minutes left, so only really good comments from now on. No more phoning it in. Actually, we're almost done. Does anybody have a comment on Bayesian optimization? So I know experts, well, I mean, thanks for yours. Anybody want to elaborate? So Karpathy just kind of mentions it, then that he says he doesn't use it. I know that in Goodfellow's textbook, he says it sometimes fails catastrophically, and there's no reference for that.
It's not bad when you have continuous parameters. Like when it's a continuous upper parameter, that's not, it doesn't suck that much. It's actually pretty good. The tricky bit is when you have discrete hyperparameters, like how many layers or whatever.
Okay. So now we've done our random search to find the best hyperparameter configurations. The last step is the one he called squeezing the last juice out, or gave it some funny name. I've called it ensembles and long training sessions because that's what he actually gives as advice. So the idea of ensembling says if you have models that make errors independently and you combine the predictions of those models, you'll typically end up with something better than any of the individual models. So he says that ensembles are a guaranteed way to gain 2% of accuracy on anything. So that's a personal guarantee from Andrei Karpathy. And one problem you get when you're using ensembles is now you're combining lots of potentially very big neural networks. So you have a problem with computation and possibly prediction time. And his advice for that is to use distillation, which is this technique of kind of doing a student-teacher training of a smaller neural network. So often you can get that small student network to perform as good as, or almost as good as the very large ensemble that you're using to train it.
What's his accuracy guarantee for distillation?
4%. I don't know. He didn't guarantee. He didn't guarantee anything with distillation. So maybe more controversial than ensembling things is long training sessions. So He says that these networks can keep training for unintuitively long times. The example he gives is going on winter break or something for a couple of weeks and leaving a model training that whole time. And then when he got back, it was the state-of-the-art model in that field. Sounds expensive. Yeah.
So just a practical question. So does that mean that when it stops improving and it's getting worse, and the validation set, do you still let it run, or could it come down again? Is that what he's saying, or
yeah?
So no early stopping.
So he's saying, well, it might be worth trying. Yeah. So it could be that things plateau for a long time. Your training, your loss no longer is decreasing, but then it starts decreasing again after a long period of time. I'm not sure if he's saying that if it starts increasing, so now you're overfitting, if it will then go back. But I assume he doesn't pay for his own computing, so he'll just say, yeah, do all the computing you want. Have Tesla pay for it.
On that topic, like there's actually an interesting recent-ish paper that kind of challenges the bias variance trade-off recently in the context of neural networks. So, but that might make more sense for the reading group. It's a fairly long paper.
Is he contradicting himself here because with the early stopping, and now he's telling us to train longer?
Yeah, so early stopping is a general purpose regularization technique. So you can do this and do early stopping in that you can save checkpoints. So you have your model and you have it checkpointed at various epochs.
Right, so he's saying to try both and just take whichever one works.
Yeah, so you do your really long training session, spend an infinite amount of money on computing, and then at the end, you've saved all the checkpoints, you can decide which checkpoint you actually want to use.
And if you autodraw those checkpoints, you'll end up with a really good model.
Yeah, that's true.
You'll get your guaranteed 2% right there.
Yeah.
And if you pick your absolute favorite checkpoint out of 1,000, you have optimization bias.
Yeah. Okay. So we're at the end. So we've done the whole recipe. This is my summary slide. So it's all stuff we've seen before. The purpose of the recipe is to take leaky abstractions and silent failures very seriously. Make sure you're building from simple to complex. And proceed using the scientific method. So in order to understand how your model's training and what sort of bugs you have that are preventing your model from training well, you create hypotheses and then test them, and that will tell you how to fix it, or it will tell you that you need to come up with more hypotheses. And the recipe, to summarize again, step 1, become one with your data, understand your data really well. Step 2 is set up the end-to-end skeleton and do some baseline models. Step 3 is overfit. Step 4 is regularize. Step 5 is tune your hyperparameters. And then step 6 is build ensembles and try out really long training sessions.
I would say instead of becoming one with the data, become one with the actual use case.
Yeah. Become one with the use case. Yeah, there's still people getting ready with the microphone.
Oh, sorry, one more question.
Thank you.
Did I miss something, or did he not mention error analysis at all?
I didn't mention it. I'm not sure if he mentions it in the blog. But yeah, you're right. That might be a bit of an oversight. But he's not explicitly mentioning error analysis, but the whole way through he's validating what he's doing step by step. So there's a lot of it sort of worked in to the narrative of the blog post. Sorry?
Can we even do error analysis in neural networks? Did I miss like a big paper? Since I'm talking about like Bayesian sort of.
Oh.
Yeah.
Yeah, so the question is, can you do error analysis? So there's two senses of error analysis. One is you're looking at the mistakes that your model makes. So that's one type of analyzing your errors. And then there's error analysis like understanding the uncertainties of the predictions coming out of your model. So I think your question was about looking at the mistakes that your model makes to try and get insights about how you might improve it. And I think that piece is not explicitly mentioned, but I'm sure he is doing things like it.
Actually, one of the things I've found extremely useful is if you know your classes in a classification model and if you know of obvious confusions, your model should actually be making those obvious confusions. That's actually a really cool way to debug that your model is actually learning something. So I would use error analysis as a debugging tool, at least.
Can you give an example?
In speech, the digits 1 and 9 sound very similar. So in a digit recognition problem, that's an obvious confusion I kind of look at. Again, sound classes, liquids like I and oi kind of confuse very often. So I've always looked at confusion matrices, and they serve a good purpose.
Yeah.